in a world. All right, so this is lecture 41, 9.6, real gases, and this is it, the very last one. So, PV equals nRT is the ideal gas law. Ideal gases are, very well behaved. Real gases, not so much. You can get some significant deviations from ideal behavior, depending on what gases you're talking about. One way to measure the deviation from ideality is through Z. A different Z, it is the compressibility factor. So Z is PV over nRT. You'll often see it written in other ways, but PV over nRT for an ideal gas, that's equal to 1. Because for an ideal gas, PV is equal to nRT. So if you can measure the compressibility, and it's possible to do so, and measure how it deviates from 1, then you are measuring the deviation from ideal behavior. So it's a useful measure for that all by itself. So we can look at it. For example, here. There's another picture in your textbook. This is showing it for a single gas. So your ideal gas is the horizontal line in the middle. It's the black line, just the ideal gas. Then you have a real gas at various temperatures. So the red line is at negative 100 degrees Celsius. So you can see it deviates a lot from ideal behavior. Then you have the green line at 25 degrees Celsius. And then you have the blue line at 600 degrees Celsius. Okay. So you can see the blue line is closer to ideal behavior than the red line is. Now, a couple of things to take away from this. First, look at the deviations. They go below 1, where PV is less than nRT, but really only for the coldest gas there. They all go above it, so PV is greater than nRT for all of those gases. The other thing I want you to notice is the scale down on the bottom. That's the pressure, and it goes from 0 to 1,000. So this is over a huge range of pressure, 1,000 atmospheres. Okay. So that's what we're measuring deviation from ideal behavior on, is at hundreds of atmospheres. So one of the big takeaways here is that at typical temperatures and pressures, you can expect most gases to behave pretty closely to the ideal gas law. Hopping into my lecture notes for a moment, here's another one. And now instead of comparing a single gas at different temperatures, we're comparing lots of gases at all temperatures, or all at the same temperature, excuse me. But again, it's going from 0 atmospheres to 1,000 atmospheres. And some of these gases deviate from ideal behavior more than others. So hydrogen is probably the closest to ideal behavior. It's the straight orange line there, but even it deviates. The one that deviates most strongly would be the yellow line. I don't know if you can see that. It's the one that deviates negatively the most down there at the bottom, the yellow line. But even it comes up at higher pressures. So what do these deviations mean? What does it mean for Z to be less than 1? What does it mean for Z to be greater than 1? And why do some gases deviate more than others? And why do they deviate at different temperatures in different ways? If Z is less than 1, then PV is less than nRT. Okay, what that means is that you have significant interactions. What I mean by that is that the particles are, they're not ignoring each other. Remember, that was one of the laws in kinetic molecular theory, was that gas particles only interact through collisions. That's not the case for real gases. The particles do interact. So what happens is that you get attractions between the particles that decrease their pressure and volume, causing PV to be less than nRT. Okay? So attractions. And you may have noticed from those two graphs that those attractions were more significant at lower temperatures. You didn't really see those at higher temperatures. And you didn't see any sort of attractions there at all for hydrogen gas. Okay? But you saw a lot of it for carbon dioxide. Okay? So hydrogen, no significant interactions. And the same was kind of true, it was less true, but still kind of true for, oxygen and nitrogen and methane. Okay? So those are all a whole bunch of nonpolar molecules, but then you had CO2. Big interaction. And why is that? Well, it's still nonpolar, but carbon, oxygen with those double bonds, partial negative, partial positive, partial negative. It's a nonpolar molecule overall, but it still has regions of negative and positive partial charges. So it could still interact in those ways, even though it's nonpolar. So that is one of the ways you can get deviations from ideality, is through interactions, specifically through attractions, which is what you start to get at low temperature. Okay, so low temperature is where you're going to start to see the particles interacting through attractions for one another, and that's going to cause a negative deviation from ideal behavior, where Z is less than 1. But you can also get positive deviations. Z is greater than 1, where PV is greater than nRT. And those, you'll notice, happen more at high pressure. Okay? So what's happening at high pressure is that the particles are all being squeezed together. They don't have a lot of space. Okay? You have a lot of gas particles packed into one spot. So what's happening is now you're getting repulsions. Okay? So that's one thing, significant interactions in the form of repulsions, not attractions, but repulsions. The other thing you're getting is volume. Remember, another one of the laws of kinetic molecular theory is that particles don't take up space, or that the volume of the particles is negligible compared to the total volume of the container. And at high pressure, that's no longer true. Okay, volume of the particles, not negligible. So suddenly, what that means is that a particle can't move through a space if it's occupied by another particle. So at low pressure, the volume occupied by those other particles is negligible. You can ignore it. But at high pressure, you can no longer ignore the space occupied by the other particles, because there's just not much space left overall. So those are the two ways you can get deviations from ideal behavior. So ideal equals high temperature, low pressure. Real is equal to low temperature or high pressure. Okay. So those are the two regions where you can see deviations from ideal behavior. And low temperature means Z is going to be less than 1. High pressure means Z is going to be greater than 1. So you're going to see ideal behavior at high temperature and low pressure. Why high temperature? The particles are zipping around too fast, no time to interact. And at low pressure, they're too far apart. So whereas at low temperature, the particles are sluggish, they're moving around slowly, they have plenty of time to interact. And at high pressure, they're just too cramped together. Okay? It doesn't matter how fast they're zipping around, they're just in each other's faces all the time. Now, there are some equations flying around out there so that you can model real gas behavior. We're not going to go into those. They're interesting. They explore real gas behavior in different ways. But I don't think there's a whole lot of point to making you practice that sort of algebra. It's just interesting from a more theoretical standpoint than from a math standpoint. So remember, ideal behavior at high temperature, low pressure, and real behavior at low temperature or high pressure. And that is that. I'll see you for the review.